Take two. One thing I should mention is because a significant portion of the possible grades that you can get are based on writing, if you are not comfortable with your writing abilities in English, that will become a problem, just FYI. I know students in the past that had English as a second language and weren't that comfortable writing. It affected their grades quite a bit. So there's that. Any other questions? Okay, so last time I think we were talking about traveling salesman problem. Is that where we ended last time? Is that right? Yeah. And we were talking about how, I mean, just with 100 cities, we would have more possible permutations than there are particles in the universe, which is crazy. We could take each hydrogen atom and take a permutation and align them, give each particle a permutation, and we'll run out of particles, which is mind-blowing. Now, there are ways to reduce that number, don't get me wrong. The point really, though, is, and those of you might remember, you know, we talk about these like big picture approximations, right? Of like what the complexity is. So, I mean, checking if the traveling salesman problem is a valid traversal is easy, right? And calculating the total distance of a particular permutation, that means a traversal, is easy. You just go and calculate the distance between each, add them all up, and you're done. And that's like a linear time thing, right? It's easy if the distances are all pre-computed. If not, you might have to do some like distance calculations, but if you have everything pre-computed in a distance matrix from every city to every other city, it's going to be easy to calculate the Euclidean distance. And we also said, yeah, of course, we could like, if you gave me every single permutation that there is, every possible set of ordering of cities, and I take the algorithm of calculate the total distance for each of them, all I have to do then is select the ordering that gave me the smallest Euclidean distance. That's it. It's easy. That's trivial. The problem here comes up when we consider the fact that, well, how many permutations are there? So sometimes calculating these things can be easy, but when optimizing, well, the model, the thing that we're using to calculate the distance was easy, the model, but looking for the input, the size of that input space is gigantic. The size of the possible permutations is huge. So for any instance, we know the model, just calculate the total cycle length. We know the output, it's the cycle length. So the key now is to find the order, the input, that gives us the desired output. Shortest possible path. And if there's a tie, whatever, it doesn't matter. Pick one. And this is where the optimization comes in. Like you figure, really, I'm searching if, okay. This is a very difficult problem. Does anyone in here know what class of problem this is? It's a fairly advanced question, I suppose.
Is it something like, I don't remember exactly, like N1 complete?
It is NP hard.
Oh.
Which is, I'll talk about this again in a second. This is something you would cover in your theory of computation course. It's a class of problem where there exists, or there does not exist any known algorithm that can operate in polynomial time to solve this. And it also has a special catch that we also don't have a polynomial time algorithm to verify that it's like the correct, the optimal or something as well. So this is a very difficult problem, yeah.
So there's nothing that's in polynomial time that can solve it, but like if you were to employ something like Deich's algorithm to solve this, would that be just as inefficient then as like,
well, so that right there, if you were to do Dijkstra's, you would have to do quite a few modifications to get that working here. But I know what you mean. You're just talking about like, well, aren't there just like maybe heuristics? Because Dijkstra's a heuristic. Are there heuristic algorithms out there for traveling salesman problem that can get you a, you know, it's not going to get you the optimal, but maybe a really good one? And yes, there are. There are heuristics. One thing I'll emphasize here about traveling salesman problem, it in and of itself isn't necessarily a particularly compelling problem, but it is the quintessential classic problem to talk about because we can easily understand what the problem is. Everyone knows what it is. And it's really hard. Now, you know, if you come up with a great algorithm that gives a really good result here, chances are it's going to be a drop in the bucket of noise of everyone solving traveling salesman problem, right? Usually when we're using these complex algorithms like evolutionary computation, we're using them on very difficult problems. Traveling salesman is one of them, but another difficult problem might be finding nonlinearities in fMRI data, in relationships there, right? That's perhaps a more compelling problem than TSP, but we like TSP as our toy problem for learning these strategies because it's easy for us to understand what the problem is. You know, the model is simple, the output is easy to interpret, minimize the total distance. The input is easy to think of, it's just permutations, right? So don't think that traveling salesman problem isn't, I don't want to say it's not interesting, it's interesting, but understand it's a bit of a toy problem for learning. But it is of the class of very, 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 very hard problems. So, yeah, FYI. Yeah, so, like, if you gave me, imagine a line. Imagine you started over here, and you gave me the first permutation, right? And again, remember, like, the cities that we were showing, you know, they're labeled like Toronto, New York, whatever. But we're going to relabel them and just give them a number. 0, 1, 2, 3, all the way to 99. So we've got 100 in total, 0 through 99. If we start at the beginning, we'll start with permutation 0, 1, 2, 99, right? And then the next one, and then the next one. Imagine we've got this nice linear ordering of these permutations. Really what I'm doing is when I'm optimizing, I'm searching through, and we really don't need to think of this as a linear collection. We could just think of it as a giant bag full of permutations. I'm searching through those permutations. A word we'll often use when doing this type of stuff is searching the space of possible permutations. And you can kind of even think of that, like gradient-based search is really popular. I mean, a lot of neural networks use gradient-based stuff. And a gradient, that's just a fancy way of saying like following slopes. So if I'm looking for the warmest spot in this room, and I'm standing here, I might feel around and be like, you know, it feels a little cooler over here, and it's warmer over here. Where should I go? Probably, you know, that way. You know, maybe it's a little warmer up here, and then, I don't know, it's actually right over here. The idea is, I'm searching this physical 3D space for the warmest spot. With TSP, I'm searching through the space of all possible permutations for a really good one. Hopefully the best, but I'm not even going to bother with that. I'm just going to look for a good one, because that is a tractable problem. Hopefully, is finding a good enough solution. It might not be the best, but when you've got 100 cities, a really good solution quickly is a lot better than the optimal solution in longer than the universe has existed. Right? So that's the realm of problems we are talking about. 8 queens. Here's another classic one. Raise your hand if you've heard of this one. Cool. So the goal of this problem is you have an 8 by 8 chessboard, and yes, this problem can be generalized to larger chessboards. So we can call n queens, where it's an n by n chessboard, and there are n queens. But here it's 8 queens. I have 8 queens and an 8 by 8 chessboard. And my goal is to place them on that chessboard such that they can't attack each other. They're all safe. And let's look at that one. It looks like it looks good, right? I don't think there's any queen on there that isn't safe. Right? Looks good? Yeah. So, in this particular example, if I was optimizing, well, this one's a little different. With TSP, I wanted to find the optimal. This one is a little bit different because there is no optimal. There might be a lot of valid solutions. So to me, in this problem, I'm just looking for a workable solution, a correct solution. And so this is actually a little bit of a different class of problem than TSP, because TSP, we can't verify that we have the optimal in polynomial time, but here we can verify that we've got an admissible solution in polynomial time. It's easy, just check, right? So it's a very complicated problem, but this one's a lot easier to verify the correctness of, because I just need a working solution. You know, it's a very discrete binary scenario in terms of the output. Is it admissible or is it not admissible? So here, that's not so much, here I guess it's kind of tricky to optimize, right? There's no gradient. You know, with TSP, it's, you know, if I have a permutation and I make a small change in the permutation and it gets better, I might be like, oh, okay, all right, I like that, let's follow that. Here, well, what would that be? So yeah, place E, yeah. So we know the model, we know what we want. What's the input? A configuration of queens. Here we just need an admissible solution. Now, if you had, here's a quick question that I'm getting a little bit ahead of myself in terms of the course content, but it's just a little thought experiment. And I know I talked about this last time a little bit with TSP, but if I'm trying to encode traveling salesman problem, I mean, the traveling salesman problem, and by the way, it's called traveling salesman problem historically and conventionally it's still called that, but we can call it traveling salesperson problem. Doesn't matter. Well, for us, we'll consider them the same. So for the traveling salesperson, how would you encode the permutation? Right? How would you, this is a real world thing. I've got these cities at latitude and longitudes, probably defined by their centers of the city, whatever, I don't know. But they have latitude and longitudes, and I need to define the traversal. My encoding is probably going to be just a permutation, right? I'm going to make it so, if I have cities 0 through 99, I will have cities 0 through 99, and then I'll just shuffle them. Right in there, there's a permutation. I can shuffle them again, there's a permutation. But they're permutations. Each city is unique. I could encode a solution, a path, that is just random numbers between 0 and 99, but then we might get duplicates. And if there's one duplicate, well, then we're going to miss a city. And that won't be an admissible traveling salesman problem solution. Because, well, we need to hit every city once and only once. So we could encode it one way or another way, but one might have some advantages over the other. We put a constraint on our encoding such that it makes the space of possible combinations a lot smaller. Right? So if I have permutations of 100 cities, or if I just have 100 numbers where they can all be 0 through 99, which group is the smaller? That would be like 100 to the 100, right? Right? I think 2 to the That's a big number. So the permutation, although gigantic, is not as bad. With n queens, all right, I've got an 8x8 chessboard. Well, here's an encoding that might work. Create an array of arrays, 8x8, and I don't know, put zeros and ones in them, right? That would work, right? It's just, it represents the chessboard. That might be what I would call a fairly direct representation, because it's easy to go from the encoding to like what the problem is. Right? I've got an 8x8 board, zeros will be everywhere, and wherever there's a queen, I'll put a 1. Right? Why not? That'll work. But maybe we can come up with a slightly better encoding. That might, once again, reduce the search space to a subset that might be a better subset to search. And we'll revisit this. So optimization. See this little thing right here? That's a little antenna. That little antenna. So think about this. What is my model? Well, I guess this is getting a little tricky, right? Like, well, what do I want? Well, I have signals that I want to be able to send. Someone over there wants to be able to receive those signals, and we want to design this antenna such that it optimizes the throughput and effectiveness, the signal transmission, whatever word I should use. This right here, would you have ever, like, imagine you're an engineer who's been trained in antenna making for 50 years. Do you think any engineer trained in antenna making for 50 years would come up with that thing? Maybe, but I'm gonna guess no. I'm gonna guess no because what the hell is that? And it's tiny too. But that antenna was designed by an evolutionary algorithm. And it works. It's in space. There's other stuff on space too. So now modeling. So I was talking about optimizing. Modeling is a little different. Or we could think of it as the same if we put a bit of a spin on it, and we'll come to that. But modeling, so remember we talked about simulation already, I think. Maybe I didn't. We will talk about simulation. Pardon me. So modeling. When modeling, we know the input, we know the output. If the model is good, if we can like map our inputs to outputs in a way that we're happy with, maybe we're happy with that model. So this right here, the iris example, is the quintessential, one of the first little machine learning problems you'll probably explore. Raise your hand if you've seen this before. Bunch of people. It's a very simple problem. Well, here's the problem. Imagine you're a botanist, and you've got a billion pictures of irises coming in. And each one of these irises can be classified into either iris versicolor, iris setosa, or iris virginica. Assume I'm pronouncing those well. So each of these images coming in, or let's not even have them as images. Each data point coming in as an iris can be classified as one of these three things. But there's going to be a lot coming in. It's going to take me a long time. So maybe I'm going to turn to machine learning to make my life a little easier. Because I could, like these three different types of irises, I mean, just by looking at them, you can kind of get a sense of their differences. So for each of these irises, I'm going to make 4 measurements. Their petal width and length, and sepal width and length. And I don't know if I'm pronouncing, is it sepal, sepal, anyone know? Sepal, there we go, I'll have to remember. So the sepal length and width as well. So we have these 4 values. Just think of it as like a vector of just these 4 floating point numbers. Wouldn't it be great? So now imagine I said, here is a giant text file CSV of those vectors. I've got each row is that length 4 vector, length, width, and each row is an observation of a particular flower, and each column is like petal length, sepal length, right? So I've got this like table, and each row corresponds to one specific observation of one flower. And I said, based on this data, write some code, a bunch of if statements or something, to tell you which class it is of these three. It's going to be a pain in the ass, right? I mean, you could probably do it, tinker away, hack at it. Wouldn't it be great if you could just tell a computer, hey, here's a bunch of data, and here's a bunch of known answers for some of that data, right? I have a 4-dimensional vector, but maybe for the first 150, I've gone through and annotated them as like, okay, yes, this one right here is a setosa, and this one over here is a versicolor, and this one over here is another versicolor, and so on. So for the 150 of them, I have a label. I know what the correct classification is. Wouldn't it be great if I could tell the computer, hey, here's the inputs, here's their class, figure it out. And then it just magically does, right? With a simple machine learning algorithm, maybe like K-nearest neighbors or something. Raise your hand if you've heard of K-nearest neighbors before. A couple people, good. K-nearest neighbors is a really simple machine learning algorithm where I'll discuss it just because it could be good to know where all of the stuff we're learning falls. If imagine I only had length and widths, so it's 2-dimensional, right? So for each flower, I had length and widths of the petal, right? If I plot those length and widths, I might have like, okay, well there's one, and X will be like versicolor. And then let's see if I have another color. Black, green, perfect. And then over here I've got a whole bunch of setosas. And I'm just plotting them on this 2D plot based on their length and widths. And then over here I've got a bunch of virginicas, right? This is a very idealized scenario. Real world data is much grosser than this. But if I come along and give you another data point that you've never seen before, let's see if I can find a better color. No. All right. If I come along and give you another data point, and it's right here, which class is it probably going to be? The green triangle, right? Why? Because it's closer to them. If it looks like a dog and it barks like a dog, it's probably a dog, right? That's the idea of that algorithm, and it's great, it's simple. A funny thing, people like to geek out. I am just as bad, okay. Me, as a person who studies evolutionary algorithms, is as guilty as anybody. In the world of AI, machine learning, heuristics, and all that stuff, computer scientists love to geek out about our complex algorithms. We love it, right? In reality, no one wants these complex algorithms. If you have a problem and you can pump it to K-nearest neighbors, that's amazing. If it works well, fantastic. Why? Because if your boss says, hey, your boss who has a degree in business management comes to you and says, oh, yeah, I need you to classify these flowers. And then you do it and you come back and you're like, oh, I built this neural network, it's got all these layers and blah, blah, blah. And they'll be like, well, how does it work? You're like, well, okay, first we need to talk about gradients, and then if you say, I don't know, this, they'll be like, oh, I get it. This is very explainable AI. Have you heard the explainable AI? That's like a buzzword these days. Yeah. So we like those simple algorithms. Things that are explainable, we love those things. So modeling here is the search for, in this case, if it's just like a simple function for classifying these flowers, it's a search for a function that gives us really good, correct classifications. By the way, if at any point anyone has any questions, if you've ever had me before, you know I like to answer questions. Yeah, okay. So modeling is optimization. So we talked about optimization, and then we talked about modeling. And the funny thing is we can think of modeling as an optimization problem. Before, when we were talking about TSP, we were searching the space of inputs, where the inputs are the permutations. But if I'm looking for that model for classifying flowers, well, I mean, I don't need to search the space of inputs, right? Because, I mean, you're just giving me those inputs. The goal is to come up with this way of telling you what the class is. So if you could imagine for a second, remember, when we were talking about TSP, or finding the warmest spot in the room, I was talking about traversing the space of those permutations. Searching the space of this three-dimensional room for the warmest temperature. Here, when modeling, and we're thinking of it as optimization, anyone want to take a guess at where we're optimizing? Like what space we're searching through? Someone mumbled something. Was it you? Who was it? You? Who said it? I can't hear. What did you say? Complexity? I think I know where you're going with it, but that's not the word I'm looking for. What I'm looking to do is search the space of all possible models. All possible configurations of a function that would give me that output. Now, chances are, I don't want to search the space really of all possible models. I want to constrain that space to models that might be reasonable. Like having a model that just prints out versicolor every time, probably not a good one, right? So maybe I won't, I could probably trim some of those possibilities down to make the space a little bit smaller so it's easier to work with. But at the end of the day, we're not searching the space of permutations. I'm not searching this. I'm searching the space of possible models. And what the model is will be context dependent. What was your question?
Well, I was going to ask, if you are able to cut down the implicit domain of functions that you're choosing from, how can you make a reasonable choice of what functions to do without trying them all? And if that's the case, then how is that actually an improvement?
It's complicated, and we are going to that right there is a theme that will be covered throughout. Some of them are going to be easy, like n queens. Maybe we shouldn't allow two queens to be in the same row or column. Immediately, we know that would be an inadmissible solution, right? And that's easy to check. So suddenly, I've cut down the search space quite a bit, and I haven't affected the ability to get the optimum, or pardon me, an admissible solution. For the model space, if you think of all possible programs out there, a lot of them are probably crap, right? Some programs say, hello world. That's not something worth considering. So we want to make sure we're finding a subset that, one, is constrained enough that we're not wasting time, but also inclusive enough that we're not excluding possibly really good solutions. So that fuzziness is a problem that's going to, I mean, if you carry on doing anything data-y, that fuzziness is going to haunt you for the rest of your life. So the question you're asking, it's a complicated question. That's a big question and a good question. So, okay, we can frame modeling as optimization, simply treat the model output as the input of an optimization problem. Okay. Yeah, okay. So just imagine like optimizing the model as the input to the test of how good it is. This is perhaps overkill in trying to visualize it. Just know that we can sometimes think of modeling as an optimization problem itself. Yeah, so this is trying to remember. This right here is a really good model, and the model is just simple math, relative, that describes someone doing a motor task moving their tongue, their fingers, and their feet in an fMRI, right? So that's what that one is. Now the reason I show you this is my PhD focused on this type of stuff. But the problem that I was interested in during my PhD was finding nonlinear relationships in fMRI data. So the funny thing is, your brains, every single one of you is a computational system. And each and every one of you is, I would assert, at least as powerful as a Turing machine. Who here knows the formal definition of a Turing machine? Crap. Well, doesn't matter. Basically, it means you are at least as powerful as, like, those computers. Now, there's an asterisk there because Turing machines technically need to have an infinitely long tape, but I get around that by saying a sufficiently large tape. For those of you that don't know the definition of a Turing machine, this isn't going to make much sense. But either way, we could say we are at least as powerful as, like, that computer, right? But the funny thing is, we can do nonlinear operations. What's the absolute value of -2? What's the absolute value of 2? If I told you to plot absolute value function, f of x equals absolute value of x, you could do that, right? Just big B. That's it. Yeah, that's a nonlinear function, and you and I can look at that and recognize it. I could probably show you the plot without telling you what the function is, and you could tell me that's absolute value, right? That's a reasonable thing, right? A bunch of people probably would have been like, that looks like absolute value. I could even complicate it a bit and like add 1 to it or something, but you'd be fine with that. That's a nonlinear function. It's a very simple one. It's got like point nonlinearity, but it's nonlinear, and you're all capable of understanding that. You're at least as powerful as a Turing machine. You could all simulate a Turing machine if I gave you a sufficiently large tape. You could do it. The point of that means your brain would then be a nonlinear system, like Turing machines that we would call like nonlinear computational system. So there's nonlinearities in the relationships of what's going on in your brain. So your brain is full of neurons that connect to one another, there's ion pumps, and there's potential differences that make the neurons fire, and there's all this stuff going on, but your brain is just this gigantic network of crap that are, firing, and it does everything you do. How those things relate to one another must have nonlinearities in there. The relationships between different parts of your brain must have nonlinearities if you're a nonlinear system. I would not be able to find a linear, if I was only looking for linear relationships in your brain, and I wanted to model your brain with only linear relationships, very simple things, multiplication and addition, right? Just think of your linear models. B1 plus x1, no, B1 times x1 plus b2 times x2, and so on and so on and so on. Your simple linear thing. Y equals mx plus b. If you're looking for things of that nature to describe the brain, you're not going to find it. But that's what neuroscientists do that study fMRI data. They only look for linear relationships. The trouble there is, those linear relationships cannot possibly describe the brain and how those relationships take place, how they happen, why they happen the way they do. So, I used evolutionary computation to search the space of models that was not just linear, but could be nonlinear. That's a fancy way of saying, I don't know, there's crazy nonlinears in you, here. Right? There it is, just trust me. In fact, this wasn't even a particular, this is a really early one. I got way better models later on. Point being, I had to resort to the big guns to be able to find something like this that describes the relationships in this person's brain when doing a motor task. So I wasn't searching the space of only linear models. I wasn't searching the space of all possible mathematical models. But I had this constrained space and I searched through it for a good one that described the relationships going on in the brain. So this is another use of evolutionary computation. Pretty cool one if you ask me. But perhaps I'm biased. And then there's simulation. If you know the input, you know the model, just run it, see what happens. Yeah. So you do this when real world alternatives might not be feasible, such as what would happen if we simulate a volcanic eruption on a small island in the Pacific with 1 million people living on that island? You're not going to be able to run that experiment. So, maybe we simulate it or something. And if your model's good, hopefully it tells you something good. If you, raise your hand if you took 161 with me. If you're modeling, we simulated the zombie apocalypse, right? Right? Why? Well, because we can't really run a zombie apocalypse. So we simulated it and saw what happened. So when optimizing your modeling, we're trying to find a particular thing, an object within a space of possibilities. So we call this the search space. So here, let's say we have something called fitness, where fitness is some measure of goodness. The values there are arbitrary, it doesn't really matter. But if I'm trying to optimize fitness, let's say I'm looking for the biggest possible number. Depending on what the values of trait 1 and trait 2 are, whatever they are, as you change what those values are, you can get a different fitness value. So let's say I'm looking to somehow maybe magically find, so this is like a 2D plot, but then we had the third dimension, which is just the fitness, okay? So let's say I've got this interesting function. I don't really know what it is, but I have this function called f of t1, t2. It's kind of faint. Can you see this at the back reasonably well? Yeah, I'll use not green next time. Where when I plug in to this t1 and t2 into this function, if I'm doing an optimization, let's say, maybe I know what the model is. Maybe it's like t1 plus t2 divided by 75 plus 1 billion. I don't know. Some stupidly simple little mathematical expression. And maybe my goal is optimizing. Find the t1 and t2 that gives you the biggest number from that model. So, as I play with the different values, I get different fitness values. So, we're exploring this two-dimensional space to find a point in that space that results in a good fitness value. Is what I'm saying making sense? Or not? Or at this point you're like, yeah, I know, get it, move on. So I'll just carry on at my pace then, okay. So if I'm looking for, there exists a T1 and T2 that gives you the best possible fitness value, let's say. You know what, we could start even easier. I'll pick a different marker. I'm going to come up with, this is going to be a really stupid example, but it's going to be a correct example. If I gave you the function f of x equals -1 times x squared, right? It's upside down parabola, right? And I told you, now let's say you're a computer and you're dumb. You can't look at this and go, oh, it's just an upside down parabola. That is an upside down parabola, right? I'm not lying. It better be, otherwise. So if you're a computer and I said, all right, go find the optimum. All right, and I can go, okay, let's start with 7. I plug it in and I get a number. That's like my fitness. I plot 8, see what happens. Oh, okay, all right, well that changes. I could plot every single one of those points on a Exactly, yes, absolutely. So this is the space for if I'm trying to optimize the value that comes out of f of x, then this is it. I can just keep trying, I can keep looking for different x's until I'm happy, until I somehow pick 0 and go, oh, that's awesome. 0 is the biggest number here because everything else is more negative than it. Do we agree with that statement? It's a very simple one. It's a one-dimensional problem. I have one value, I've got a knob, and I'm turning it, and I'm looking for the best thing. You ever turn into a radio station and you're like, kind of like doing that, right? That is like a two-dimensional version. I've got two knobs, and maybe I'm looking for the optimum. So I want to find the configuration of T1 and T2 that gives me the best possible thing. Maybe that space is huge, and I just need something that's good enough. So that would be optimizing like the inputs, like looking for that value. But alternatively, what if I happen to know that plot where I have 3 data points? I have trait 1, trait 2, and the fitness score, whatever that means. So imagine I've got this like 2 inputs and I know the output. Imagine I start with this. This is the output, right? I start with this and I start with this, but I don't, or I start with that. And I have some function. And I've got a big set of x's, right? I mean, I could just pick any possible x value. But I don't know what this is. So maybe the goal is to come along and try to change this. Change what that expression is such that the inputs map as accurately as possible to this. I want to be able to put in -1 or 1, and whatever this expression is, and again, I don't know what it is, I'm trying to find it. But if I know this plot, I know that when I give this -1, it magically gives me the output -1. If I give it 1, it magically gives me the output -1. 2, -4, and so on. I know that. If I have a model here, if I've got some magic, function here, I'm magically looking for this. I want to be able to keep changing this thing such that when I plug the numbers in, they fall exactly on this line. This would be analogous to the classification problem. I know what the class is of all these things, of all those flowers. And I have all those flowers. Come up with a magic way of just telling, like figure out how to tell me that this does map to that. Right? Any questions? Because it's gotten quiet, which is always concerning. Like it's gotten real quiet to the point that I always think like, have I lost them? I am somewhat skipping a little bit ahead. This is still fairly introductory, and I'm just kind of sprinkling the more advanced ideas. So hopefully as we go, more things get filled in. So the search space can be enormous. TSP, yeah, it's huge. If we're building a decision tree, you've heard of decision trees before, kind of like just follow a tree structure down and see what to do. Like, should I play tennis? Is it raining? Yes or no? No. Is it too hot outside? Yes or no? No. All right, play tennis, right? That's like a decision tree. Just think of like those yes and no. But if I'm building this giant decision tree, I mean, in theory, that decision tree could go on forever. It could be like infinite, right? So these could be very big search spaces. Framing things as search problems is awesome because, I mean, think of our problem as the space of all possible solutions. It might be a weird thing to do, but when we're looking for, if we're optimizing or looking for a model, if we think of it as searching a space, I don't know, to me it just kind of makes sense. Some of those spaces might be very high dimensional, of course, so it's hard to visualize, but I always like to bring it down like, so imagine I'm looking for the warmest spot in this room, right? I want to traverse this room. Maybe there's some interesting features about the search space, the shape of it, that might give you a hint towards what algorithm would be good to use. If you saw something like this, you'd probably go, I just want like a hill climber. If your space is crazy like that one I just showed, good luck, because it's all over the place. And we can think of a solver. Okay, yeah, so the problem is a search space, like traversing a search space, and the mechanism which we solve the problem is some way to traverse that space, some way to walk through that space in a way hopefully gets me a good solution. If it's the temperature, I'm probably going to follow like a temperature gradient. You know, doing that might not give me the optimal solution. I might not find the warmest spot in the room. To do that, I would have to hit pause on the universe, start up there and just measure at every point, right? But if I'm just doing this like greedy, just go towards the warmer parts, I might get stuck on like a local optimum. Where yeah, it's warm here, and in this part of the room, this is the warmest spot, but really the warmest spot's right over there. But I didn't find it because, you know, I got to here, which is the warmest spot, but then everywhere else around me is small. So I was kind of on this like hill, even though there's a bigger hill over there. But I couldn't see that bigger hill because the space is just gigantic. It's really far away. The question then, gotta keep an eye on the time. Oh man, good thing I looked. Okay. The question then is, what's a good way to move through the space? How much further do we have? All right, quite a bit. All right, that's cool. We'll pick up here tomorrow.